Today, I want to introduce a new way of thinking about intelligence. Not intelligence as memorization, not intelligence as pattern matching, and not intelligence as predicting the next token, but intelligence as adaptive scientific reasoning. This project is called ASRA, Adaptive Scientific Reasoning Architecture. At its core, ASRA is an attempt to build systems that can enter completely unfamiliar environments, explore them, form hypotheses, discover hidden mechanics, and invent strategies dynamically. The central idea is simple. Real intelligence is not knowing the answer beforehand. Real intelligence is figuring out how to discover the answer when the world is unfamiliar. That is the kind of intelligence ASRA is designed to pursue. Most modern AI systems are trained to recognize patterns inside distributions they have already seen. But human intelligence, and perhaps generalized intelligence itself, works differently. A child can enter a completely new environment and begin experimenting. A scientist can encounter an unknown phenomenon and start forming theories. An animal can adapt to unfamiliar terrain without memorizing every situation beforehand. That is fluid intelligence. Fluid intelligence is the ability to invent strategies in unfamiliar situations. Static intelligence says, I know this pattern. Fluid intelligence says, I don't know this environment yet, but I can figure it out. ASRA is fundamentally about building systems capable of that second form of intelligence. Modern AI systems are incredibly powerful, but most of them remain heavily dependent on training distributions. They perform well when the environment resembles their data, but once the environment changes significantly, reasoning becomes brittle, strategies collapse, exploration weakens, and abstraction transfer fails. Why? Because most systems are optimized for prediction, not adaptive discovery. They recognize correlations, but they do not truly understand unknown mechanics. When action meanings are hidden, when objectives are unclear, when rewards are sparse, many current systems struggle to adapt. ASRA is designed specifically for those situations. ArcAgi represents one of the most important benchmarks for generalized reasoning. Why? Because it removes the comfort of memorization. The environments are unfamiliar, the mechanics are hidden, the action semantics may be unknown, and the agent must discover the rules through exploration. This transforms intelligence into an active scientific process. The system must observe, experiment, infer, adapt, and generalize, not from massive memorized datasets, but from interaction itself. ARC is important because it tests whether intelligence can emerge through adaptive reasoning rather than static recall. Large language models are extraordinary systems, but fundamentally, they are passive predictors. They generate tokens based on learned statistical structures. That gives them enormous linguistic capability, but reasoning inside an unknown interactive world requires something additional. Unknown environments require experimentation, feedback loops, memory evolution, causal inference, adaptive planning, and dynamic world model construction. Language alone is not sufficient. An intelligent system must be able to act, observe consequences, and update its internal understanding continuously. ASRA attempts to bridge that gap. From passive prediction to active scientific cognition. ASRA treats reasoning as a scientific process. Every intelligent interaction becomes a cycle of observation, hypothesis formation, experimentation, evaluation, and model refinement. This is deeply important, because intelligence may not fundamentally be about storing answers. It may instead be about building mechanisms for discovering answers. In ASRA, the agent behaves almost like a scientist inside an unknown universe. It observes patterns. It tests assumptions. It refines beliefs. It constructs causal understanding incrementally. The architecture is inspired not by static computation but by adaptive discovery systems. The core philosophy of ASRA can be summarized in one sentence. Intelligence is the adaptive invention of strategies in unfamiliar environments. This changes everything, because now intelligence is no longer measured by benchmark memorization, static performance, or parameter count. Instead, intelligence becomes adaptability, abstraction, exploration, uncertainty handling, and strategy synthesis. ASRA is designed around the belief that genuine reasoning emerges through interaction with the unknown. ASRA is not a single model. It is a cognitive architecture, a coordinated ecosystem of reasoning systems. Different components specialize in perception, memory, hypothesis generation, planning, exploration, world modeling, and strategy formation. This modular approach is critical, because intelligence itself may not emerge from one monolithic mechanism. It may emerge from the orchestration of multiple adaptive cognitive processes working together dynamically. ASRA therefore behaves less like a static neural network, and more like a scientific reasoning organism. At a high level, ASRA operates as a continuous adaptive loop. The environment produces observations. Those observations are interpreted through perception systems. The agent constructs internal state representations. Hypothesis systems begin forming possible explanations about the environment. Exploration planners decide what actions are most informative. Memory systems store experiences and abstractions. World models attempt to simulate environment behavior. Strategy generators synthesize action policies. The agent acts, and then the entire cycle repeats again. Over time, the architecture gradually transforms uncertainty into structured understanding. The first challenge in any unfamiliar environment is perception. The system must determine, what am I actually looking at? ASRA's perception layer focuses on extracting meaningful structure from raw observations. This includes object segmentation, spatial relationships, pattern decomposition, symbolic extraction, and environmental feature identification. The key idea is that perception should not simply encode pixels. It should transform observations into reasoning-compatible representations. Because higher reasoning depends heavily on how the world is internally represented. Once observations are perceived, the system must build an internal representation of the environment. This is the state representation layer. The purpose here is abstraction. Raw observations are compressed into structured semantic representations, symbolic graphs, relational structures, spatial hierarchies, and latent state embeddings. The architecture attempts to answer, what are the important variables governing this environment? Good state representations reduce complexity while preserving causal structure, and this becomes foundational for planning and reasoning. One of the hardest problems in adaptive intelligence is hidden action semantics. The system may not know what actions actually do. An action labeled Action 1 might move left, rotate an object, trigger a hidden mechanism, or perform something entirely unexpected. ASRA treats this as a causal discovery problem. The system performs controlled experimentation. It compares pre-action states, post-action states, and environmental transitions. Gradually, the architecture builds internal mappings between actions and consequences. This allows the system to infer action meaning dynamically, not from prior labels, but from experimentation itself. Exploration is one of the most essential aspects of intelligence. Without exploration, there is no discovery. ASRA uses adaptive exploration mechanisms driven by uncertainty estimation, curiosity, novelty detection, and expected information gain. The goal is not random movement. The goal is strategic experimentation. The system asks, what action would teach me the most about this environment? Over time, exploration transforms unknown spaces into structured cognitive maps. Memory is not simply storage. Memory is accumulated structure. ASRA separates memory into multiple forms. Episodic memory stores experiences. Semantic memory stores generalized concepts. Procedural memory stores strategies and action patterns. Abstraction memory stores reusable reasoning structures. This layered memory system allows the architecture to remember experiments, reuse discovered strategies, transfer abstractions, and accelerate adaptation in future environments. Memory becomes the bridge between exploration and intelligence. ASRA continuously generates possible explanations about how the environment works. These are hypotheses. The system may hypothesize hidden rules, causal relationships, reward structures, environmental constraints, or action mechanics. Importantly, ASRA does not assume certainty. It maintains competing possibilities simultaneously. Reasoning therefore becomes probabilistic and adaptive. The architecture behaves more like a scientist evaluating theories than a classifier selecting labels. The core reasoning cycle inside ASRA resembles the scientific method itself. Observe, hypothesize, experiment, evaluate, update, repeat. This loop is central, because intelligence emerges through iterative refinement. Every action becomes an experiment. Every environmental transition becomes evidence. Every failure becomes information. The system gradually transforms ambiguity into understanding through recursive interaction. As exploration progresses, ASRA begins constructing internal world models. These models attempt to predict state transitions, hidden dynamics, causal effects, and future possibilities. The architecture is essentially building a simulation of the environment internally. This is crucial for planning, because intelligent systems must eventually reason about what would happen if I tried this. World models allow imagination, counterfactual reasoning, and strategic foresight. Once sufficient understanding emerges, ASRA begins synthesizing strategies. This is not memorized policy execution. This is strategy invention. The architecture combines observations, world models, abstractions, and environmental constraints to generate adaptive action sequences. Importantly, strategies remain flexible. The system can revise strategies dynamically as new information appears. This is critical for fluid intelligence. ASRA includes meta-reasoning capabilities. The system reasons about its own reasoning process. It monitors uncertainty, confidence, exploration efficiency, hypothesis quality, and planning effectiveness. Meta-reasoning allows the architecture to decide when to explore, when to exploit, when to revise assumptions, and when deeper reasoning is required. This creates adaptive cognitive control. Goals themselves can evolve dynamically. Higher-level goals generate subgoals. Subgoals generate experiments. Experiments generate new information. ASRA therefore uses hierarchical adaptive planning. Instead of following rigid objectives, the architecture continuously restructures priorities based on environmental feedback. This creates flexible long-horizon reasoning. Fluid intelligence is the ability to solve unfamiliar problems without memorized solutions. This is one of the central ambitions of ASRA. The architecture attempts to transfer reasoning structures, not fixed answers. That means adapting to new worlds, inventing strategies dynamically, and learning abstract principles transferable across domains. Fluid intelligence may ultimately depend more on adaptive reasoning mechanisms than on static knowledge storage. Statistical prediction asks, what pattern is most likely? Scientific reasoning asks, what mechanism explains this behavior? This distinction is fundamental. Prediction can succeed without understanding, but adaptive intelligence requires causal reasoning. ASRA attempts to move from correlation-based cognition toward mechanism-based cognition. Pure neural systems are powerful pattern recognizers. Symbolic systems are powerful abstraction engines. ASRA combines both. Neural systems handle perception, representation learning, and pattern extraction. Symbolic systems handle logic, structure, causal relationships, and compositional reasoning. This hybrid approach attempts to achieve both flexibility and abstraction simultaneously. ASRA is designed to improve through recursive interaction. The architecture learns which exploration strategies work, which abstractions transfer, which reasoning paths fail, and how to reason more efficiently over time. This creates the possibility of recursive cognitive refinement. The system gradually improves not just its answers, but its methods of discovering answers. Although ASRA aligns strongly with ARC-style environments, the architecture is broader. The same principles could apply to robotics, autonomous scientific discovery, biology, adaptive simulation systems, and open-world reasoning agents. Any domain involving uncertainty, hidden dynamics, and adaptive interaction can potentially benefit from this framework. ASRA can be implemented using a modular systems architecture. Core technologies may include PyTorch or JAX, reinforcement learning, graph reasoning systems, vector memory databases, planners, world model simulators, and transformer-based reasoning modules. The architecture is designed for extensibility. Different cognitive modules can evolve independently while participating in a unified reasoning ecosystem. ASRA can also be viewed as a multi-agent cognitive ecosystem. Different agents specialize in exploration, memory, evaluation, planning, and hypothesis testing. This mirrors distributed cognition. Instead of one monolithic reasoning process, multiple cognitive subsystems collaborate dynamically. This can dramatically improve adaptability and scalability. Traditional AI evaluation often focuses on benchmark accuracy. ASRA instead emphasizes adaptation speed, exploration efficiency, strategy invention, transfer learning, and performance in unseen environments. The key question becomes, How quickly can the system understand something fundamentally new? That may be one of the most important measurements of intelligence itself. ASRA aligns naturally with ARC, AGI. 3. Because the benchmark emphasizes exploration, hidden mechanics, adaptive reasoning, and abstraction transfer. The architecture is specifically designed for environments where rules are unknown, action semantics must be inferred, and strategies must be invented dynamically. Rather than treating ARC as a static puzzle dataset, ASRA treats ARC as an interactive scientific reasoning environment. Imagine entering an unfamiliar environment. At first, the system knows nothing. It begins exploring carefully. It observes changes. It compares states. It tests actions. It detects patterns. It forms hypotheses. Gradually, the environment transforms from chaos into structure. Then strategies emerge. This entire progression, from ignorance to understanding, is the essence of adaptive intelligence. ASRA is not only about benchmark performance. The larger vision is adaptive scientific intelligence. Future systems may autonomously conduct experiments, build scientific models, reason about biology, design materials, explore physical systems, or operate in unknown robotic environments. ASRA is ultimately about creating systems capable of discovering structure in the unknown. Nature Foundation models aim to build AI systems capable of understanding the laws and structures of nature itself. ASRA acts as the adaptive reasoning engine inside that broader vision. It provides exploration, hypothesis formation, causal reasoning, and adaptive cognition. Together, these systems aim to move AI from passive prediction toward active scientific understanding. Decision biology asks a profound question. How do living cells process information and make decisions under uncertainty? Cells continuously sense signals, evaluate noise, adapt behavior, and make survival decisions. In many ways, cells themselves behave like adaptive reasoning systems. ASRA's reasoning principles align naturally with this perspective. Because biology may fundamentally be an information processing system operating under uncertainty, the future of AI may not simply be conversational systems. It may be scientific intelligence infrastructure, systems capable of understanding nature, simulating environments, generating hypotheses, conducting adaptive experiments, and discovering previously unknown structures. ASRA is one step toward that direction. A framework for adaptive cognition in uncertain worlds. The future of intelligence may not belong to systems that memorize the world. It may belong to systems that learn how to discover it. Systems capable of exploration, abstraction, experimentation, adaptation, and scientific reasoning. ASRA is an attempt to move toward that future, toward intelligence that behaves less like static computation and more like adaptive discovery itself.